Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 36, Uranus and Neptune. So in this lecture, we will finish our tour of the major planets in the solar system by looking at the last two gas giant planets, Uranus and Neptune. One of the things that makes Uranus and Neptune special is that they had to be discovered in modern times as they weren't visible to the ancients. You might remember from our discussion of the calendar that the planets Mercury, Venus, Mars, Jupiter, and Saturn were all visible with the naked eye, easily visible with the naked eye, and so they have been known since ancient times. We don't know who discovered those planets because they are so easy to see in the sky that people have always known about them. But with Uranus and Neptune, they had to be discovered. So let's talk about their discovery first, or at least the discovery of Uranus first, and then talk about them as planets. So the discovery of Uranus begins with the astronomer William Herschel. So William Herschel began life as a musician, and he was a talented musician. He moved from his home in Germany to Bath, England, to play music, and here's his home in Bath, England. And in Bath, England, he took up a hobby of astronomy. Now, William Herschel did astronomy with his sister Caroline. She was his constant companion. While he was looking through the telescope, she would write notes and take extensive notes on what he was seeing. On evenings that he could not observe or wasn't up to observing, she could observe with the telescope. She was an excellent astronomer in her own right. Unfortunately, throughout history, her contributions have mostly been downplayed compared to her brother William's contributions, but she was an astronomer in her own right that certainly made significant contributions to the field. One evening in March of 1781, Herschel was surveying double stars in the sky. Now, what that meant was he would park the telescope at a part of the sky and he would let the sky drift by. And as the sky drifted by, he would report to Caroline what he was seeing, and she would write down in their logbooks what it was that her brother was seeing in the telescope. And on March the 13th, 1781, an interesting object moved through the field of view. It was an unusual star because it clearly showed a disk. Through even the biggest telescopes in the world, stars always look like little tiny points of light. But here was something that didn't look like a star at all. It looked like a little tiny disk. Now, that could be a comet, for example, because comets are usually fuzzy, but could show a disk like this. So Herschel decided that he would come back and follow it for a few nights. If it was a comet, it would be moving through the sky. So he followed it for a few nights and found that, in fact, it was moving through the sky, and he believed that he had discovered a comet. But when he reported his discovery to others, as they monitored the motion of the planet, they realized that it was too far away. Using Kepler's laws of planetary motion, they were able to calculate where it was in the solar system and how fast it was moving, and realized and convinced Herschel that what he had discovered was not a comet at all, but in fact, a new planet in the solar system, the first planet ever to be discovered. Now, Herschel decided that he wanted to call this star Georgium Sidus in honor of King George III. As you can imagine, that wasn't very popular throughout the rest of Europe. I'm sure it certainly wasn't popular here in the colonies, which of course is King George III is the king that the colonies fought against in the Revolutionary War. So on the continent, it was given the name Uranus. Georgium Sidus was actually used in Great Britain up until the 1850s or so, when they finally abandoned that and adopted the name Uranus that everybody uses today. So that is the story of the discovery of the planet Uranus. So a little bit about Uranus. It is 19 astronomical units from the sun. It takes about 84 years to orbit the sun one time. It is barely inclined to the sun compared to the Earth's orbit around the sun. Its inclination is only 0.7 degrees. Its orbital eccentricity is a fairly circular orbit, 0.046. It's 4 times the diameter of the Earth, and it's 14.6 times the mass of the Earth, and its density is 1.2 grams per cubic centimeter. Now, what's interesting about Uranus is its rotation period. It's not 17.2 hours, it's minus 17.2 hours. That minus sign indicates that Uranus rotates backwards. The truth is a little bit more complicated. Uranus is actually tilted over on its side. It's tilted over with respect to its orbit around the sun by about 98 degrees. Being tilted that far over means there are times in its orbit when Uranus's north pole is pointed at the sun. Half an orbit later, its south pole is pointed at the sun, and in the intermediate times, the sun is over the equator on Uranus. But because the tilt is a little bit more than 90 degrees, we say that its rotation is retrograde, that it is rotating backwards with respect to its orbit around the sun. So that is the planet Uranus. Uranus, when seen up close by spacecraft, looks like a featureless blue ball. Now, it's important to know that Uranus has been visited one time, and that was by the Voyager 2 spacecraft in January of 1986. So the Voyager 2 spacecraft, after having visited Jupiter and Saturn, was able to go on and visit Uranus and fly past Uranus. Now, the blue color comes from the fact that both Uranus and Neptune, which also is a mostly featureless blue ball, have methane clouds on them. The temperatures and the composition of Uranus and Neptune produce the formation of methane clouds, and methane itself is a terrific absorber of red light. So we get all the colors of the sun coming down into the atmospheres of these planets. We get the red light and we get the blue light, but the red light is absorbed by the methane in the atmosphere, and the blue light then travels deep into the planet where it is scattered off of the methane cloud tops. And so what we see when we look at Uranus and Neptune are these featureless blue planets. And the reason they're featureless is because the action is going on down below. Any action is going on down below the methane cloud tops. Any banding or other clouds are going on below the methane cloud tops. And it's blue in color because, again, the methane absorbs the red and only the blue light gets scattered back to us. Okay. That is Uranus. I'm not going to talk much about its interior structure other than to say that Uranus and Neptune both do not have the metallic hydrogen cores that Saturn and Jupiter have. And that's because they're just not massive enough to squeeze hydrogen to the point that it becomes metallic hydrogen. And for that reason, Uranus and Neptune do not have magnetic fields that are nearly as strong as what we find at Jupiter and Saturn. The moons of these outer planets are very interesting. They are, for the most part, made of water ice, icy worlds. A beautiful example of this is Uranus's moon Miranda. Miranda is 480 kilometers across. That's about 300 kilometers from side to side. It's only the fifth largest of Uranus's moons, but it's one that's worth calling out because of this absolutely chaotic terrain on the surface. Miranda is fascinating because a small world just 300 miles across should have cooled off long ago. But clearly there are regions on Miranda that are ancient, that are covered in craters, but regions on Miranda that have hardly any craters at all. This is an example of an active icy moon. Now, again, because it's so small, before we visited Miranda, we would have expected that it would have had an old and ancient surface. Because it is so small, it wouldn't have any plate tectonics. It wouldn't have any volcanic activity. It would have cooled off long ago. But here is a world where the ice is clearly being reworked, and reworked in very dramatic fashion, because you can see ancient areas of Miranda adjacent to very active areas which have clearly recently been resurfaced over, that have far fewer craters on them than the older areas with very, very sharp boundaries. Why Miranda looks like this is unknown. Two hypotheses that have been put forward is one, that it suffered a titanic collision in its early history. I think that one is not as commonly cited these days. The more popular idea is that we are looking at a tremendous planet-wide episode of melting and flowing of water ice across the surface, probably water ice and ammonia across the surface. Miranda may have entered into a resonance with one of the other moons of Uranus. That means the two of them, their orbital periods were equal, even numbers of one another. Integer numbers of one another. That's the term I was looking for. They were integer numbers of one another. And that could have raised tidal stresses on Miranda that reworked the surface of the moon. One of the more spectacular features on Miranda is Verona Rupes. Verona Rupes is a cliff system on Uranus, and these cliffs are 20 kilometers or 12 miles high. Now, because the moon is so small, just 300 miles, 480 kilometers across, the gravity is very weak. And these cliffs, though 20 kilometers high, the gravity is weak enough that you could actually jump off the top of these cliffs and fall down to the surface. And you would have a slow, gentle fall, slowly accelerating. And as you got to the bottom, you'd be traveling fast enough that you'd need to do something to slow yourself down, but you wouldn't be traveling crazy fast when you got down to the bottom of these cliffs. Uranus, like Saturn, is surrounded by a ring system. But unlike the spectacular ring system of Saturn, the ring systems of Uranus and Neptune consist of a few braided knots, a few braids of icy material in orbit around the planets. So these are the rings of Uranus. They were first discovered when a star passed behind Uranus and its rings. We were observing the star from Earth to watch the star pass behind the planet. But before the star passed behind the planet, it unexpectedly dimmed a number of times, and then it went behind the planet, and then as it came out again, it dimmed unexpectedly again. And those dimmings before it went in and when it came out, those were caused by the rings of Uranus blocking the light from the star. The rings of Uranus are narrow braided strings of icy material. The most substantial of Uranus's rings is actually kept in place by two shepherd moons. A number of ring systems in the outer planets have these shepherd moon systems. And what happens with these shepherd moons is remember that the moon that is closer to Uranus is orbiting faster than the ring particles are orbiting. The one that is further away is orbiting slower. So imagine you are a particle in the ring and you wander a little bit too close to Uranus right here. As this one orbits faster than you, it comes out here, it will pull on you and it will speed you up and it will put you back out into the ring out here. On the other hand, if you wander out in this way, you are orbiting faster than this moon. As you catch up to this moon, it will pull you backwards and slow you down and you will fall back in there. So these shepherd moons, the gravity of them in a very complex interaction is responsible for keeping the material in these tightly formed rings. So that is Uranus. Let's talk now about Neptune. And first, let's talk about the discovery of Neptune. So Uranus was discovered in 1786. In 1781. By the early 1800s, it appeared that Uranus was not following Newton's and Kepler's laws of motion. It appeared that Uranus was speeding up and then slowing down as it orbited the sun. Now, one possibility was that Newton's laws of gravity were wrong and that Kepler's laws of planetary motion were wrong. But a number of mathematicians and astronomers thought that another possible explanation was that there was another planet in the solar system, and that planet was pulling on Uranus. Because it would be further out than Uranus, Uranus would be catching up to it, so Uranus would initially experience an acceleration, and then when it passed that planet, it would experience a deceleration. The first person to believe this was John Couch Adams, a young mathematician in Great Britain. Adams used the speeding up and the slowing down of Uranus to calculate the position of where Neptune, where this new planet, he obviously didn't know about Neptune, where this new planet would be in the solar system. He made these calculations and then he felt he needed to show them to someone. So he took them to the Astronomer Royal in Great Britain. Unfortunately, when he brought them to the Astronomer Royal was busy at the time and said he would look at them later and either forgot about them or decided not to look at them because he didn't really know who John Couch Adams was. Many years later, when Uranus was discovered, he went back and looked at Adams' calculations and found that Adams was exactly right. Adams had predicted where Neptune would be in the sky. But this wasn't known until after Neptune was discovered. Completely independently, a French mathematician by the name of Urbain Le Verrier had also used the exact same technique. He'd noticed Uranus speeding up and slowing down and used that to calculate where Neptune was. Now, Leverrier went to the Paris Observatory and told them that he had predicted that there should be a new planet in the solar system and told them where that planet would be, but it turns out the Paris Observatory was busy with a major project at the time. They didn't put much stock in his calculations, and they decided not to break away from their project and told him that they couldn't undertake the search at that time. So Leverrier wrote to Johann Gottfried Galle at the New Berlin Observatory, which of course is now an old observatory, but at the time was the New Berlin Observatory, and reported to him that he had calculated that there should be a new planet in the solar system. So that very night that Galle received the letter from Leverrier, he used the telescope at the New Berlin Observatory and began his search. And this was in September of 1846. And that night, on September the 23rd, 1846, Galle at the Berlin Observatory found the new object within 1 degree of where Leverrier had predicted it would be. So this was the discovery of Neptune. But most important of all, this was a tremendous confirmation of Newton's laws of gravity and Kepler's laws of planetary motion. Because although it was thought that they might be broken because Uranus wasn't following them exactly, it turns out they were exactly right. The gravity of an additional planet that we did not know about was pulling on Uranus. And in fact, Neptune exactly explained this discrepant motions in the planet Uranus. And it was a brilliant piece of evidence that Newton's laws of motion, Newton's law of gravity was correct. So Neptune was discovered on September the 23rd in 1846. Neptune is about 30 astronomical units from the sun. Its period is 164 years. So you can work out the numbers since it was discovered in 1846 and its period is 164 years. Neptune has orbited the sun just a little bit more than 1 time since it was discovered. Its orbital inclination is only 1.8 degrees and it's in a very circular orbit with an eccentricity of just 0.01. Its diameter is a little less than 4 times the diameter of the Earth, but its mass is 17.2 times the mass of the Earth. So you'll notice those two numbers are interesting. You'll remember that Uranus was a little bit more than 4 times, well, it was about 4 times the diameter of the Earth. So Neptune is a little bit smaller, but it is also more massive. And that comes from the fact that Neptune is much denser than Uranus. Neptune has a density of 1.6 grams per cubic centimeter, and it rotates on its axis once every 16 hours. Neptune, like Uranus, mostly presents a featureless blue sphere. There were discovered in the Voyager 2 spacecraft. So Voyager 2 flew by Neptune in August of 1989. Cloud bands were visible in the atmosphere of Neptune. There was a great dark spot, like the great red spot on Jupiter, that was visible. But otherwise, it was mostly a featureless planet. So we can see some of these high, thin clouds on Neptune. These clouds are hundreds of kilometers wide, and they stretch for thousands of miles across the surface. They're about 30 miles or so above the cloud deck down below. These thin clouds. So you can see here in this case, that was determined by looking at the shadows. So we can see the thin clouds and their shadow below. So how far the shadow was separated from the cloud tells us their altitude. It was about 35 miles above the clouds below. What's interesting about the great dark spot on Neptune is it was believed that it was similar to the great red spot on Jupiter. And since the great red spot on Jupiter has persisted for hundreds of years, if not being a permanent feature, it was believed that the great dark spot on Neptune must also be a permanent feature. So surprisingly, just 6 years later, when the Hubble Space Telescope in 1995 turned and looked at Neptune, everyone was surprised to see that the great dark spot had disappeared. So remember that Voyager flew by Neptune in 1989. These images were taken in 1995, just 6 years later. And by that time, the great dark spot had disappeared off Neptune. So the great dark spot is clearly something that comes and goes on Neptune. And again, it is something that warrants additional understanding, additional observations to understand what's going on. And then with Neptune, it also has a thin ring system, similar to the ring system of Uranus, which consists of just some thin bands of icy material. One of them, pictured by the Voyager spacecraft, clearly shows braiding almost like rope as the icy particles are braided in a thin band. Neptune's largest moon, Triton, is one of the most interesting moons in the solar system. So the first and most important thing to know about Triton is that it orbits Neptune backwards. All of the major moons in the solar system orbit in the same direction, the prograde direction that their planets spin. Now, a lot of the small moons of, say, Jupiter and Saturn orbit the planets backward, and that's probably because they're captured asteroids. But all the major moons orbit in the same direction that the planets spin, with the exception of Triton. And that gives us an indication that Triton may actually be a captured object. It was probably not formed with Neptune, but was captured at some later time. Now, Triton is an absolutely fascinating icy world, and it is probably a good indicator of what the icy worlds of the Kuiper Belt look like, because it is probably a captured Kuiper Belt object. There's lots of interesting terrain, like this cantaloupe terrain that we see on the surface here. Down in the southern hemisphere there are geysers of what appear to be water-like material jetting into the sky and getting blown by a gentle wind and falling back to the surface. But most interesting on Triton is evidence of cryovolcanism. We see flows that look like volcanic flows on the surface, flows that look like they have filled in impact craters. The problem is the surface of Triton is far too cold, and it's an icy body. It's not a rocky body. The flows that we're looking at are cryovolcanism, flows of water and ammonia across the surface. In fact, these pits may be volcanic pits, but not where liquid rock has flowed out, but liquid water and ammonia have flowed across the surface in this amazing cryovolcanism. Those geysers at the pole down here are probably, again, water and ammonia geysers being thrown into the air and being blown by the wind and falling back to the surface. Triton is the perfect introduction to the next body that we will study in the solar system, and that is Pluto. Pluto is the largest body that we know of in the Kuiper Belt right now, and it too is an icy body like Triton. So in our next lecture, we will pick up with Pluto.